Good evening, ma'am. My presentation theorem is the primes of q omega can be decomposed into three classes. First, 1 minus omega and its associates. Second, the rational primes of the form 3n plus 2 and their associates. And the third is the prime factor of the rational primes of the form 3n plus 1 and their associates. Then proof. Let pi be a prime of q omega. Since q omega equals to q under root 3 is a simple field. Pi divides exactly one rational prime, say p. Then we distinguish the following cases. Case first, when p equals to 3. Now we know that 1 plus omega square equals to 0. So omega cube equals to 1 and minus omega square equals to 1. Since 3 equals to minus omega square into 1 minus omega square. Since q omega is a simple field, every rational prime can be decomposed into at most 2 primes of qw. Now minus omega is a unity and 1 minus omega is not a unity. So 1 minus omega must be prime of q omega. So case second is when p congruent to 2 mod 3. If possible, let p be not a prime of q omega. Since every natural rational prime in q omega can be decomposed into at most 2 primes in qw. There exist primes p o pi and eta of q omega such that p equals to pi eta. Then p square equals to n pi n eta. Consider n pi. Now only positive factor of p square are 1 p square, which implies n pi equals to 1 or p square. If n pi equals to p 1, then pi is a unity of q omega. Contradicting pi is a prime of q omega. If n pi equals to p square, then n eta equals to 1. Then eta is a unity of qw. Contradicting eta is a prime of qw. So we must have n pi equals to p. Let pi equals to a plus b omega. So a plus b into under root minus 3 minus 1 upon 2. So n p equals to n pi equals to 1 minus b by 2 whole square plus 3b square upon 4. So p equals to 4p equals to 2a minus b whole square plus 3b square equals to 2a minus b whole square mod 3. So p congruent to 2 mod 3, which implies 4p congruent to 2 mod 3. So first is not possible for any value of a and b, which is contradiction. So p must be prime of q omega. So case third, when p congruent to 1 mod 3. Here we claim that p cannot be prime of q omega. If possible, let p be prime of q omega. Then let p equals to 3n plus 1. If n is odd, then p becomes an even number greater than equal to 4. Therefore p cannot be a prime. So n must be even. So p equals to 3m plus 1 for some m greater than 0 and m belongs to z. Then minus 3 is a quadratic residue of p. There exists an integer x such that x square congruent to minus 3 mod p. or P divides x square plus 3. But Q omega is a simple field, which implies P divides x plus 3 under root minus 3 or x minus under root minus 3 in QW. Either x plus P plus x by P plus 1 upon P under root 3 or x by P minus 1 upon P under root minus 3 must be an algebraic integer of Q omega, which is not so. So P cannot be a prime of Q omega. So P must be divisible by a prime of Q omega. Thank you.